In this Plait program, I have a container data type that has one variant called bin, whose field needs to be a number. So of course I can say bin1, and that gives me a container, but if I say bin true, that will fail because true is not a number. If I write quote A here, then remember that something like quote A is really a question mark. So now I can write bin1, and the decision has been made that this is a container of numbers. If I try bin true at this point, then it fails because the constraints worked out that quote A had to be a type number. Contrast this to f here. So f, at first I've declared it to be a number, so I can call it with 1 and I can't call it with true. But if I put a quote A here, then it turns out I can call f on anything. I can call f on 1, and I can call f on true, and both work. And that is because the type of f is not resolved to either number or Boolean. Plait has inferred a polymorphic type for f. It says pick an alpha, and then give me a value of that alpha, and I'll give you a list of alpha back. The difference between the function definition and the type definition is that Plait can insert effectively a big lambda around that other lambda. If we want to make container similarly generic, then what we have to do is explicitly say we want containers of alpha. And now with this definition of container, I get to pick every time I use bin. I can make a bin of 1, or I can make a bin of true. Notice that the type is not merely container, but it's now container number or container Boolean. In fact, it would be better to write container of. That would follow better the list convention and box convention and so on. So now I say bin1 and I have a container of number. But once again, if we go back and we take this away, then it doesn't matter that I put of in the name. When I do bin1, it's now forcing all container ofs to have numbers. And if I do true, then it fails. Notice that if I do things the other order around, if I say bin true, then now containers can take booleans, and then when I do bin1, then it doesn't allow a number. So what's going on here? If we look at just the type of bin, we can see what's going on. The type of bin, it looks kind of like a polymorphic type, but there's this underscore here before the A. And when we have quote underscore something, that means a type variable in the inference setting of something that hasn't been unified yet, as opposed to a type identifier that means a polymorphic variable. As soon as I use bin on 1, then this quote underscore A, this type gets unified to numbers, so that if I look at bin again, now it claims to have type number to container of. So underscores are stateful things that can change as more expressions become available to type check, whereas actual polymorphic types, like making a container of alpha here, if we now look at the type of bin, we'll see that it has a quote A without any underscore. Even after I use it once, that doesn't change the type of bin. And I can mix these things together. I can say that f takes not just an A. Suppose I want f to take a container. So we can declare the type of x to be container of A. And if I look at the type of f, it's container of alpha arrow list of container of alpha. I can pass f a container that has a number in it, or I can pass it one that has a Boolean inside of it. This quote A here, it's still really a question mark, and the type inference of Plait is just figuring out what can go there and figuring out that it can make everything polymorphic. But if I go back to if and I put list of bin1 here, now I'm always returning lists of containers of numbers. So when I look at the type of f, it says you have to give me a container of number because I always have to return a list of container of number. So that's again illustrating that this quote A is really a kind of question mark. But when we don't constrain things, then polymorphism can be inferred.